morning, everyone, and thanks for joining my talk. Today, I'm going to talk about and go into a little detail about a software that we've developed that helps manufacturers who own and manage their own spare part inventory optimize that in real time. So a little bit about me and about my company. I'm the co-founder. We're about 3 years old. We're an Atlanta-based company. Without getting into too much detail, we essentially help manufacturers and intra-facility logistics companies make smarter decisions with data. We develop tools like the one that we're going to talk about today. And we also specialize in digital twins, which is a little bit different, but falls into the same vein. Here's some of the companies that we work for. So today what I wanted to do is talk about spare parts. I do want to get into some of the weeds with our tool and how it works and give you a glimpse under the hood. So I'll describe the problem a little bit. There's a lot of data science tools out there, and I'll tell you about what we used and why we used them. And then we'll talk about how our clients use the tool and some of the things that we learned in onboarding our clients to use these tools. So a little bit about spare parts. For those who may not be familiar, manufacturers have lots of very expensive pieces of equipment, and this equipment has a number of parts on them, right? And what some of the bigger manufacturers do is they keep spare parts on hand, so if something breaks, they don't have a large disruption to their productive capacity. The thing is it's a really tough problem to track and maintain. You've got potentially several different types of machines, maybe some from even different countries and manufacturers. Some parts can be used on more than one machine. More than one machine may pull from a single part. So what we did is essentially map all these things together with the focus of trying to anticipate how much inventory we need to keep on hand for the unexpected part failures. Aside from just the mechanical complexities of spare parts, there's some other business constraints that govern how many and which parts we need to keep on hand. So you can imagine lead time. How long does it take to get a spare part if we decide we want to order more? How much space does it take up in our warehouse, and how much holding costs do we have to pay? How often does this thing fail? Does it typically fail once every 3 years, or is it every other day, right? And then how much are we going to use that machine? One thing that we see a lot of is that our clients are holding on to spare parts for machines that they don't even use anymore, products that they don't produce, or maybe they've upgraded their machines, but they haven't gotten rid of the inventory of spare parts that are designed only for that machine. So machine usage is definitely plays into there a lot. And then there's the idea of stock out cost, right? And when we take a look here on the right, the idea is that there's a happy medium here at the bottom, indicated by our happy face, where when we look at spare parts, we want to minimize the cost that this spare part affects on my business with either having too much inventory on the right side, and if you don't have enough on hand, you have a lower inventory, you're going to have too many stock outs. So there's that happy medium that we try and find, and it's a really hard problem, right? Because for some manufacturers, they've got hundreds of machines, potentially hundreds of thousands of spare parts that they keep and maintain on hand, and it's sort of ever changing as their business changes. They've got to react in the same way, but in reality the problem materializes in a way that isn't so scientific, right? When you've got VPs or people high up in the company see how much inventory they're holding in spare parts in their warehouse, it seems like low-hanging fruit to go and reduce that inventory. And so, if you have potentially, millions of dollars, people could say, well, let's reduce that. We're holding on to parts that we don't need. Let's, take it from 8 million to 4 million or whatever it is. And then it's somebody's job to go and do that. The thing is that you're going to end up, in some cases, if you're not, methodical and scientific about it, you're going to flip to the other side where, you got rid of too many parts, or you didn't hold the right parts on hand. And now you're going to be, stocking out quite often, which again means that you've got a part failure. You need to wait for, a replenishment, or find some other place to produce the products that are no longer able on the failed machine. So a little bit about our solution. I know in 20 minutes it's going to be difficult to get all the way into the weeds of how it works, but I'll just, from a high level, describe our thought process and how our solution works. So the first thing is we need to understand how to parameterize failures, right? So how do we know how a factory plan or how a production forecast will translate into part failures? So for each individual part, it may fail specifically to a given machine, or it may fail specifically to a type of product that is producing. There's a lot of complexities in that first point, but the idea is that the first step is really to understand how your production forecast will translate into part failures, and parameterizing that with a distribution based on historical data. The second part is to get your production forecast in a way that you can sort of multiply that by the first one, if you will. So, you looking in a 3 to 4 years in advance, sometimes more. We need to take sales forecasts and translate that into production forecasts and anticipate, some changes that may be happening on the plant floor itself. The third thing is really I won't call it the secret sauce of our software, but it's really where you start to get some really clear results. And the idea is that you want to simulate and create what we call theoretical futures of part failures over the next 3 years, right? In the world that we live in, we're going to only observe one projection of what is, an obviously random event. But what we want to do is simulate how our parts could fail over the next 3 to 5, 10 years, whatever it is, and aggregate that data to understand how sensitive we are to the expectations. So, for instance, if we want to say for a specific part, manually create a rule that says I want to be 95% sure I'm not going to stock out over the next 6 months, that's going to be a different inventory level potentially than if I wanted to be 50% sure or 99% sure. So the sensitivity that we have to part failures is critical to maintaining the optimal inventory. The fourth one is also kind of unique, and the idea is that planners, we mentioned some large manufacturers will have potentially thousands of parts, and the way that they typically manage these day to day is they do it through Excel, right? How many parts do I have? How many parts have I gone through in the last month or 3 years? And, do some rudimentary calculations and find out which ones they need to pay attention to. But what we can do is link to their business software. You analyze it in a more elegant way, like we talked about, and essentially tell the planners, hey, here's 3 or 5, 10 parts that we think that you should be ordering soon. Take a look, dive in, and see if you agree. So instead of them going on a wild goose chase, what we do is we essentially provide to them what we think they should be focused on. And then the fifth part is pretty simple, but we just connect all of this information and serve it to the to the users in a way that's intuitive, we think, and elegant. So talking a little bit about sort of the stack that most industrial facilities use is indicated by this graphic on the right. We don't really need to understand everything that's going on here, but if you think about the bottom row here as being the plant floor, all of this information that happens on the plant floor gets aggregated into systems above it. And there's a few different stacks, and we're just going to focus here on the level 3 and level 4. So essentially what will happen is as parts fail and as they're pulled out of the stockroom and consumed, there's typically a record of that transaction that's saved in the ERP or enterprise resource planning system. Think SAP or Oracle, right? So there's a lot of data that's already there that essentially our system can interface with, track, and sort of communicate with, so that we can make some smarter decisions. On the level 3, that's where you're getting more real-time information about this week or this month's plan. So some MES systems or manufacturing execution systems will have the production plan in them. And so what our software can do is essentially query the ERP, understand how many parts you have on hand, how much they've been used in the last 6 months or 6 years, whatever it is, and then listen to the MES system and say, hey, what's the production plan? So essentially what we want to do is not create any more work on the planners. We just want to tie into the system they're already using and give them something that's easy and ready to use, essentially. So here's a brief video demonstration of what the software actually looks like. Unfortunately, I don't have a desensitized version that I can show. Everything is protected by NDA agreements, and we take those very seriously, as you can imagine. But what you're seeing here is essentially like a React interface that's tied into a cloud-hosted, could be locally hosted backend that serves this tool. And we've got some interactive parts to each page. There's several pages here where the planner can zoom in, look over, in this case, multiple years, and see where they anticipate the part usage trending. On this middle graph here, you can see even some confidence bands, right? When we talked about sensitivity, that's important because a wide band is potentially going to be treated differently than a short band given the same center line, right? So this is what it looks like. So a little bit more about what's going on in the back end. So our solution relies primarily on the 4 packages you see listed on the top. React, everybody knows, I'm sure. SymPy, I think most people are familiar with. It's just a Python-based discrete event simulation package. We actually needed to use a C# equivalent of that package, because Python was too slow. When we're running Monte Carlo, hundreds of iterations on multiple years of tens of thousands of parts, it became like an overnight type thing, and we wanted something that could compute in a few minutes, and so that's why we did that. Some other ones that you probably may not be as familiar with, Gurobi optimization is, in my opinion, the best mixed integer linear programming solver out there that helps us balance the costs of stocking out and holding inventory, and helps dial in on the right inventory levels and the right reordering points. So that's part of that as well. And then Foreo is sort of the platform that we built on. They are a company who hosts simulation-based tools, and typically do it in an academic setting, but it worked out really well for us to have them sort of host and own and maintain the backend while we focus on just the front end of the science. A little bit outside the scope of this talk, but what I think would be an interesting discussion for later on is the idea that we're not going to have perfect data. So much of what our tool does is clean the data, data validation, right? Look for inconsistencies, look for weird things so that we don't serve garbage. And one of the things that we needed to adapt was for the ERP system, if that top layer, that level 4, right, doesn't have all the information we have, we need to use the information, the best information we have, and all the information we have to fill in the missing parts. So we did I think some pretty creative engineering to use similarities to generate best guesses for information that we didn't have. But again, that's sort of a story for another day. And that concludes my talk, and I will jump back over to the interface here and look to some questions. So please feel free to put questions in the chat, and I will be happy to answer them. So did we look into Julia? We did, but Matt, we saw that there was going from Python to C# for us made a little bit more sense from a speed point of view. I know Julia is sort of in my mind, a faster version of Python. We did look into it briefly, but decided to go C# for some of these. All right. Well, I think my time is about up. If anybody has any other questions, please feel free to email me anytime or find me on LinkedIn, richard@autointel.io, and Richard Schrade on LinkedIn. I'd be happy to connect and share more.